Okay, so let's come back to this. I found the paper, and instead of wasting your time, I read it throughout the paper as well as the abstract. There was no, maybe that's a good thing, they didn't really explain the origin of why this happens. But nevertheless, WF was used. And let me try to come back to this point of two things. I want to first say that if you don't, here is what I just is plotted differently as instead of 1 over t. So this is the bunch of data, and the smooth line is the WF. And they didn't try to normalize it so that everything, as I showed you, it will be either above it or below it. In fact, you can eyeball it and find out the WF is actually weaker. The data is steeper. So I may even have drawn it incorrectly in my notes here. Yeah, so I drew it. The WF was stronger. So either way, but you can see the point. The question was indeed what I was trying to indicate. Indeed, was trying to. This data was involving stretching to a same level. To me, that's good enough. You just stretch, as I depicted here, you just stretch to the same level to different temperature, you get this curve. And the only way to explain is this reveals an internal time scale that depends on temperature. And the only thing I can try to check on this is I know there's something that's an internal time scale, that's polymer relaxation time, the WF. So you put them together and see, oh, it looks similar. It's, okay, let's move ahead, right? So what they did is much, what? I mean, I always envy people who are this thorough. They actually did this way. For each temperature, they stretch different amount. And these are the time you have to wait for the different amount of stretching. The time to wait is shorter if you stretch it more. And so this is a curve that shows how much, if I stretch, for example, if I stretch about 400 times, I only have to wait, let's say, 100 seconds. And then if I stretch only 200 times, then I have to wait a day or a week. So that kind of thing. And they did it for different temperatures. And then this curve is horizontally shifted in a manner of revealing that experimental data shift versus the WF. So that shift is equivalent to what I described it. I simplified the matter. So it's the same thing at the end of the day, except that one does require a shift. You need a curve to shift. I was mumbling because I only have points. I cannot shift points. They actually did it for all the different strands. So it's equivalent to basically this. We'll come back to basically what I described to you quite precisely. What I described to you was just looking at one line. Okay, one stretching, and this is how much you wait. And of course, if you have a whole set, that's give you much more powerfully systematic data. In other words, these things shift the same amount as the whole curve shifts the same amount. Except that shift amount is different than WF. So pick and choose. Now we're really at the end of this game of discussing through this wonderful experiment, which sadly you don't find it's being repeated. There are more than hundreds of papers on fracture mechanics of elastomers ever since. Probably this one, I don't know, maybe this one is very painful to explain. Oh, I don't know, I'm joking now. I just don't find this. There's one comment only, which is, I think at that time, is still remember, this is, did I say it here? This is unnotched sample. Just take a pristine, innocent sample. You stretch them, no notch. Certainly up to the 70s, this breaking that eventually occurs suddenly somewhere is, of course, up to that point perceived to happen starting with flaws. So you tell me, so they are thinking about something is cooking and it takes time, or something, polymer relaxation comes back. This whole 9 yards of viscoelasticity is giving them the medicine. It's okay. That's the best I could do for you, meaning it's certain that up to 70s, we think this feature is still a matter of fracture mechanics with the stress being enhanced at the tip. But for this thing to cook into a crack, it involves somehow chain dynamics has to come in somehow. And chain dynamics is slower at lower temperatures, therefore I should wait longer. How about that? I want to be in their shoes and go with it. And this is why I keep saying today, in fact, in the lecture, Whitby lecture, it was, I wish he answered it less ambiguous, that indeed we don't all agree that there are flaws that are large enough that's important or not, but if you push them harder, many of them will say this is not a flaw problem. In other words, don't bother with flaw. Flaws are not big enough to weaken your material. Weaken to the point of lowering your strength. Okay, so I think with that, let's try to get to two parts. One is Lake Thomas. In fact, I should say two things at once. The other is Revlin Thomas, the same Thomas. So with fracture mechanics being well developed by the time of 1953, he is very well known, and of course he later is also very well known in rupture. Basically, they provided a protocol to study rubber in terms of measuring the toughness. I'm not going through the details, except to tell you that they think a very clever argument, because at the end of the day, they want to calculate so-called energy release rate, that is energy that you can release upon crack propagation per unit area. And I run out of time to describe the argument, which is a very beautiful one, but at the end of the day, they can prescribe this measurement this way, and WC is the stress. So if this is a SS curve, we call it, of a uncut sample, then your cut sample typically just breaks much earlier, right? Because you have a big cut here. And it breaks about here. And this WC is area under the curve. So it provides you an operational way to measure GC for stretchable elastomers. Remember when Griffiths developed this concept of energy release rate, critical energy release rate for window glasses, this essentially works only in the limit of linear viscoelasticity and also strain intolerant material, meaning it doesn't stretch much. Therefore, it clearly does not apply for rubber. So this is their real pioneering contribution, that they devised a way to think that you can record the energy release rate even when the sample is very stretchable. And as in this celebrated first paper on polymers, they actually was in a hurry to show that this is the same as doing tearing. Which I explained to you that this is nothing but force divided by the thickness of your sheet-like sample that you tear. And I must remark, even though this was proposed, most of the time people do tear, as I try to show you some of the literature figures that basically plot something like this. And in recent, we don't like the tear because you cannot see what happens at the crack tip. It's being teared, right? I'm still having my papers. I know you can. So with tearing, we cannot quite see that tip, what's going on. So we prefer to look at it this way. But it turns out, cut it short, you can do it this way and get a similar result by using pure shear. And this amounts to saying that this is where my sort of comments comes in. This amounts to saying that basically, in their language, the toughness or this energy release rate, I'm sorry I verbalize so much. This is called toughness and energy release rate, right? Is a growing function of how fast you tear. Or conversely, in this pure shear experiment, how fast you watch the crack to propagate directly correlate with how much you are stretching. And how much you are stretching essentially determines what level of energy release rate we will have. So at the end of the day, you have the situation of tear give you this relationship as if GC is determined by how fast you stretch. But actually, you're not controlling the crack speed. You're only controlling these two ends you are tearing. You're not controlling how fast it is. So actually, there's some instability, whatever. And what I was proposing is that the logic should be how the load is governing the propagation speed, because the load is prescribing the tension in the chain. The tension is prescribing the lifetime in the system. Lifetime determines how fast it propagates. So this is where I sometimes say F equals ma. It's better to be careful and rigorous about y versus x, because we typically learn y is the effect, x is the cause. If that's the case, I prefer we think in this way. So that's a side note. The point was that, remember, we live in this world of viscoelasticity and dissipation energy, right? So it is perceived this little dissipation independent term can occur in the zero rate limit, where there's no dissipation, because dissipation is always dependent on the rate of deformation. So Thomas was quite eager to to indicate why this G0 could be much larger than gamma. Gamma typically is only 1 joules per meter squared. So he recognized something which is absolutely influential. In fact, today, if you hear a few weeks ago that Whitby lecture, they produce papers in Science guided by this insight from Lake Thomas. Although I have a different understanding of what their phenomena is. But let me come to their model, okay? So basically, they are thinking about a crack that's growing into, into your sample. And they imagine, if you blow it up, they imagine one of this chain was breaking. And last time I even mentioned, their point was this chain that is about to break, in fact, broken by this time because you crack propagated. Actually, to be honest, I better draw this. Our lovely chain typically is wiggling, but I better draw it straight because it's really straightened already. And their idea was the energy release is not just what is associated with the breaking of this bond, but in fact, all the bonds, imagine there are many, many bonds. Many. Their idea was not only one bond dissociation will occur, release energy, but actually all these other bonds are in tension and store a lot of elastic energy in every bond. So they go back and want to calculate what should be the released energy per unit area. And in our notation, this is a piece of cake. It takes us a second to do. Because I know I draw one chain, but if you look down this way, it's a bunch of chains again, all loaded like the red chain. Looking down, right? I can always be more careful if I give me x, y, z than looking at the xy plane. Okay, it will be a bunch of red chain like that. Each chain have this much dissociation energy stored because all the bonds, each chain, did I say? Each bond is almost reaching the point of breaking. Only one bond break, but all the other bond is reaching a similar level of stored elastic energy. Let's call it E0. Or in fact, I know my notation. It was dissociation energy, we call it DE. E stands for energy, D stands for dissociation. And there are n such bonds. In a strand, because your network is nothing but a bunch of such strands, each strand is between the crosslinks, and each strand will have a size, let's call it Lx. So that's the, assuming all the strands are of the same length, that's the strand. And then how many are there per unit area? It's our quantity we have used several times, the area density. And this area density is 1 over packing length and this end-to-end distance of the strand. which this strand, of course, is proportional to the square root. Let me just try to simplify it. I don't want to go into any depths here. Basically, each of this sides is proportional to the square root of the number of bond. Gaussian chain behavior. So if you plug this thing up to there, you find that G0 is the square root of nx. And that's this is the guiding principle for a lot of people. As if your material is tougher and have a larger G0 if the strand between entanglement is longer. So for the remaining time, I'm going to switch gears and discuss about whether such a molecular model, in fact, to make sure we understand it, this Lake-Thomas model is really a monolayer model, really. It really is at a monolayer. It assumes that only a monolayer of chains are storing energy and releasing energy. I say this because we find this is probably very unrealistic. So I'm going to switch gears and come to the last part of what there is time to say. Before that, I could indicate that with this background, that you could, have no trouble. You should have no trouble understanding. There's a talk on essentially elastomeric fracture in the YouTube, and then of course I know Caroline has actually listened, has watched this recording that summarizes everything we know about mechanics of polymers, including rheology, brittle-ductile transition, and fracture. So that's just for your record and reference. You can find it beyond this class, coming back to it anytime. So let me come to the last part, which I said promised to be experimentally based. Come back to the core business of whether your sample should be regarded as a flawed or not flawed. For your polymers, how do you know? And the question of that amounts to whether that nominal strength is comparable to what you can perceive your strengths to be in absence of any flaws. Are they similar, or this is the case like window glasses? So let me remind you of two examples. We find, for example, for glassy polymers, PMMA, it is about 50 megapascals. Is it large? Well, or rather, is it small? It's definitely small compared to the fiber limit I showed you guys, which is about, let's say, make it easy. It's 10 or 15. To me, they're all the same, basically 2 order magnitude higher. Meaning the fiber limit is at least 2 order magnitude higher than what you observe. Can we blame flaw, right? Remember, this is the limit where we assume not only all the bonds undergo scission, but we assume all the bonds are bearing load, not just a network, but all the bonds bear load. Yeah. Yeah. Of course, it's gigapascal. So basically something like 2 order magnitude larger. So this fiber limit is where all the bonds bear load. So of course it's not true, except we don't know the 50 is the right, is a flaw-free limit or not. And in the case of, so this is this is plastics. And then in the case of elastomeric, we had an opportunity in the homework, actually, because I skipped describing it in detail. And the homework, again, I'm being reminded from my other class, this was one of the homework questions. Please don't use AI to do it. It defeats the whole purpose. I see I think I'm catching the end part of non-AI period, non-AI ages. My goodness, I mean, if you rely on AI, then what is there for me? Meaning, for you, what do you need to learn then, or think about anymore? So in any case, this is found to be something on the order of 5 gigapascals. Whereas in reality, again, the nominal strength, as I said, is try your best luck, you can get 30 megapascals. So again, it's order magnitudes smaller. So in both cases, there are some forces to say, man, maybe we're all dealing with fraction mechanics. They're all just flaws, and we need to invite fraction mechanics back, which has been the situation, generally speaking. But here, where it's not completely contradiction, people think that maybe indeed the number of chains bearing load any moment is only less than 1%, because the system is highly inhomogeneous in strength. Some chains are stretched, most chains are not stretched at all in the network, so they don't bear load. In any case, you can see in both cases we are not sure how to answer this question, and therefore it would be nice if you can answer this experimentally. So that's the basic point. That is, if you have a notch, for reasons that you can probably appreciate if you still remember Griffiths, the Westengard solution. Westengard solution gave us a feeling things are diverging, and you have to introduce a plastic zone to think that somehow divergence is resulting in having a plastic tip. But it's a nasty region. It may be region very small, so we don't bother to look into it. In fact, this paper is how amazing can you get? This 53 paper exactly written in the paper saying, I'm not going to bother looking at the tip because it might be conceivably very small for me to acquire any information. But the spirit is very trivial. In the spirit of English, the English basically, I reviewed for you, basically teaches you that this tip stress is much higher than load. But moreover, when the tip stress reaches inherent strength is when fracture occurs. Right? That's quite reasonable. And therefore, why don't I wait to the moment of fracture, that is at fracture, and see if I can determine what is the stress at the tip? If I can do that, then I have an experimental piece of information that allows me to evaluate this question. Right? Does that make sense to you? And it's not entirely clear why we didn't try it. Two reasons. One is we probably, let me give you speculate two reasons. One is we probably speculate this was still true. A second reason was, may I use the language of English solution? The radius of curvature might be too small, so that I cannot, I will not be able to succeed in determining the stress at the tip, because the stress at the tip would just keep building up without me being able to resolve it. Yes?
Out of curiosity.
Yes.
So, we're also talking about determining stress at tip and all of the problems. I'm just trying to think of an experimental setup that would serve to also determine stress at a nearly infinitesimal point.
Right.
And what that would look like.
Right. So, exactly. So, I'm trying to recall if I already said these two things or not. But let me repeat this and then I'll go to it. You know, so many things going on. So I start. Did I last time mention to you guys we were super, super lucky to be working with polymers? For what reason? Do you recall? Right.
It allowed us to derive more answers than something with steel, or something with a different material, because in that it was the brittle, ductile transition point serves to explain how steel works, but when you deal with polymers, it doesn't work the same.
Did I have notes even written down? I wonder. I verbalized it. I just don't know where. What did I write something here? Do you recall that our polymer is a problem when I can, for certain, say there is no plasticity in the case of plastics, and I can, for certain, say there is no viscous effect when I'm dealing with elastomers. And for folks who work with metals, they tend to yield. And they tend to do it just above BDTs. Therefore, they have a lot of sympathy for using the concept of plasticity. The same, this is why I got reminded of what I said last time. It's not easy for you to determine the stress at the tip. Let's say you can resolve it. But what method do you use for steel? I don't know of any. In fact, they must have tried if they know how to do it. But for plastics, we know, I know this is where I was just wondering how much I introduced, I'm not going to, in fact, we're running out of time anyway. But basically, so basically, we know polymers are chain-like, and when you chain-like in the sense, if you look at a single chain, they are not optically isotropic. In the sense that there is an extraordinary light and ordinary light. Depending on which way the light is polarized, it will propagate with different speed if you have a chain like this. But of course, when your chain is in the coil form, it's isotropic because it's all averaged out. So what it amounts to is, if you have a light coming in polarized this way, and then you have another so-called polarizer that only allows light that's parallel to it to pass through, then no light will pass through. Okay? So this is a polarizer analyzer, they call it. So no light will pass through. You'll be at this black point. Now imagine you have the sample sandwich between these two situations. Again, before you stretch the sample is isotropic. So on the average, these two index are the same. But as soon as you start to stretch, you start to basically cause the orientation of the electric field in the light to rotate. And the rotation gives you a projection into the horizontal direction, so light passes through. And when you use white light, because you have different wavelength, so the way they pass through depends on wavelength. So you end up spreading the different colors of the white light. And this is the famous Michael-Levy chart. Those who play with crystallization and a microscope in white light will often see this kind of colorful images. So, but cut it short, basically there is a way to tell the degree of chain orientation. And it turns out that degree of chain orientation is precisely correlated with how much you're stretching the polymer. And how much you're stretching polymer is how much the stress occurs. So it's firmly established that through this measurement, you could read the stress spatially if you have a microscope. The only thing left is the resolution of your microscope. So having said that, I just want to bring one fundamental result, and then probably we have a little time for the rubber. But basically, I think probably big enough, I don't need to play mode. So basically, this was a so in fact, I prefer you see this in the slides. In fact, what happens is if you start with the isotropic state, it's going to be black. So you're going to travel from black to gray. It's not very nice. So we could actually put a so-called retardation place so that in the isotropic state, it's already in this blue region. And as you stretch, what you already see at once is there are butterfly-like patterns here as this thing is marching on. So it's marching on to here now. And so you can, I don't know, in the play mode, does it? Yeah, so I didn't loop it. So basically, okay, let's do it beginning. So first it was here, and it passes through, okay, it's here now, and passes through, it breaks about here. And so the relationship between this color and stress can be determined. And this plot shows the result. And it's plotted as the distance to the tip, but in the form of -1/2, which means going to the tip is infinitely to the right. Okay, that's r equals 0 in the denominator. So all the basic knowledge of fraction mechanics holds that this linearity means stress is 1/r. That's exactly a Westergaard solution. And it's also the solution of the so-called Creager-Paris solution. But it's saturated at some point as you approach the tip. And this is the savior. If this thing keeps growing until you cannot resolve it, you won't be able to claim you have seen the tip stress. But it's saturated. The origin of that saturation is best understood as the fact that this crack tip is blunt. It has a finite radius instead of infinitely sharp. I mentioned once the window glasses is quite sharp, can be 1 nanometer or less, few angstroms sharp. So that's the third law of polymers. We talked about no plasticity, no viscous effect, right? No plasticity for glass, polymer glass, no viscous effect for elastomers. Third, the polymer shows a gigantic blunting of the tip, which apparently is as if we are not aware. Because if we are aware, we would have been looking for that. So to us, we were just utterly delighted that this thing saturates. And to make the story more amusing, really, truly, is saturate means what? You can read the tip stress, number one. And you find this tip stress simply increases as you load more, meaning that the nominal stress, such that the tip stress actually is growing linearly with the load, which you can express in the way of K being sigma divided by times a square root of A. And this result works all the way to the point of fracture. What is this? Remember, I once told you there is operational definition of Kc versus materialistic definition of Kc. We first saw it in experiment. And then you are reminded this result directly pops out of English solution. In retrospect, remember I introduced you in the way of discussing English solution, but we actually didn't appreciate what English was telling us until we saw experiment telling us. Okay? In other words, this linearity between tip stress and how far and how much you are stretching remotely, so-called, is linear. And this point holds all the way to the point of fracture. And since it's no-brainer to think that when the tip reaches inherent strength, in fact, so you see you have multiple messages here, right? One is this setup, as was asked. This setup, this setup was precisely, what did I do? Did something. Yeah. Maybe this will do it. So we don't know what happens experimentally, but the setup, oh Lord, what happened? I'm running out of time. So basically, this setup is crucial, right? The setup was intended to determine what is the inherent strength. If we didn't know we can resolve it or not, but apparently you can because stress saturated. And a byproduct of that is we rediscover what English solution means. And I keep insisting when you teach fractional mechanics, that should be the way to teach it. Which is really a stress-based approach. Oops, again, I did something wrong. So I don't know if you still recall, this is nothing but English result, because the English precisely was bringing this in. This is exactly English result. Except the P is a rho in the English result sense. So you can see that we got lucky multiple times. This is the third time that you can resolve it. The stress saturates, so you can claim to know what it is. And I don't have it here. So basically, the same with the elastomers. They also show a tendency in the elastomer. So we call this. So you can see this happens at about a third of a square root of r, which means 1/9 of a millimeter, which is about 0.1 millimeter. Okay, 3 basically flip that 3, so it's, trust me. So this point is about 100 micron. So by the time you are able to resolve 100 micron and smaller, you start to see the stress saturate. Get it? So with the rubber, with rubbers, you find this cutoff to be, let's say, 50 microns or even 30 microns, but still you can resolve it. Without even struggle too much, because a microscope you can 10 micron is generally the limit. So you have a window to show this stress will saturate. So so that's really the lucky situation we have. So if anything, in fact, this will summarize this entire part of. Look like this will summarize the entire part of fraction mechanics. It's all in the inside of experimentally revealed new insight. So basically, conventionally, you have this operational definition that speaks nothing about what's the magnitude of them. And through experiment, we found that you can access, since you can access the tip stress, and you basically end up being able to find that, in other words, let me rewrite it again. Tip stress is far field load times times the let me be careful on this part, the last part. So I know I cannot erase it. So basically, the tip stress, if you plot your data as a function of sigma times A, you find they are linearly related. That's this plot I showed you before. And the linearity by definition is a constant that has the dimension of square root of length, just by definition. Because on the left is the tip stress. On the right, you already have the load, and you already have the A there, which is length of the size of the cut. Then this proportionality constant reveals a characteristic length scale. It just jumped at you. And this expression works all the way to the point of fracture. So this becomes true. And this is nothing but English result. So at the end of the day, we find that this, at least to the leading order, all can be understood in terms of inherent strength. In other words, instead of this pair, it's this pair that reveals the true physics of it. And I said one more time, how sharp the tip is all where the mystery is. Which allow me to close by saying this length is not monolayer. It's much larger, which is a disaster because any molecular theory necessarily cannot come up with this length scale. Therefore, it's a nightmare in that sense. On the other hand, we at least finally know that there is a region that's very large that's involved. That explains everything, including what I started with, that this release rate would be much larger because it involves energy stored over a much larger region. Because keep it or what? Oh, I shouldn't keep it. Because this much larger region because you have high stress over a much larger region, elastic stress. that emerges near the tip. And as you break, all that elasticity will be released. So it's not involving a monolayer. And therefore, this whole thing is not a monolayer problem. And therefore, much larger than monolayer. And therefore, of course, your GC could be much larger than gamma. Lastly, I think I must say this before we close. Lastly, I don't know if you appreciated this or not. This energy approach give us the convenience that, let me just rewrite it this way, as if that or convenience or inconvenience, that I cannot perceive anything but to assign a big dissipated part as my energy release rate. A conclusion you are forced to reach unnecessarily. In the stress approach, in fact, let me write this. This is nothing but, we later found out, right, through this English kind of result, it's nothing but this times the tip radius. Look, where is the energy dissipation? None. You recall I once presented a picture for you that says this involves P. So I guess, if you don't mind my last second, so I guess even you recall that. So, and then that's all given this. Do you recall I showed this to you guys? So this is, of course, after I know the answer. This is what we finally end up having. That there is energy stored in a region much greater than a monolayer. And concluded differently too. This is not necessarily dissipation. It's just, so this gets us out of the trouble of having to keep saying that what we observe for elastomer is a bunch of process of dissipative processes, which I hammered in the beginning, that there's no viscosity process going on. Okay, so with that, I think I can close, and we can talk about maybe the format of homework.